Welcome to Computational Physics for Absolute Beginners, Episode 1. My name is Brian, and I am creating these tutorials with the goal of helping physics students who are encountering programming, coding, computation for the first time, and helping you get on board with everything you need to get started in whatever it is you're doing in your physics class using computational physics. In order to complete this tutorial, you will need access to the Python Tutorial 1 Computations and Variables. You'll need to open it in a Jupyter Notebook environment. There are different ways of getting access to Jupyter, and I will let your instructor give you that orientation as it depends on what their preferences are, what your university's requirements are, etc. But once you get into Jupyter, you'll have it open in a web browser like this, and it works just like a file system. You can click on any of the files here. We're going to start here with Python Tutorial 1, Computations and Variables, and in this video, I'm just going to walk you through some of the highlights of this tutorial. A Jupyter Notebook is composed of two types of cells. There are markdown cells. This is text that I am using to communicate instructions with you in a written format. And it contains code cells, which are where the computation code running actually takes place. For the purposes of this video, I'm going to focus on some of the code cells to help you learn how to read those. The written instructions I'm going to let you read on your own to get the necessary background, context, etc. that you need. I just want to walk you through how each of these code cells works and what they do. So the idea of a code cell is that it's a set of instructions that the computer is going to execute one at a time in order. It doesn't do everything at once. It doesn't go around randomly. It goes down line 1, line 2, line 3, etc. There are some lines that the computer will skip. Anything that starts with this hash mark, the number sign, the pound sign, shift 3, the computer will ignore. This is what we call a comment. It's where we, the humans who wrote the code, have left behind a little piece of documentation, just a little message to our future selves about what in the world is going on in this code cell. It's very important to add comments, but we'll learn more about what you do with comments later. The important thing to learn now is that these hash marks, they indicate something for you to read, the computer is going to ignore. In order to run a code cell, you have a couple of options. You can either click on the Run button up here, or on Windows, you can press Control plus Enter. But what will happen when I run this, it's going to jump down here to the output, and what it has done is taken all these lines and executed them one at a time. So let's take a look at what each of these lines would do. This first one, line 6, has a print command. Print is the way you get Python to tell you what it is thinking or tell you what it knows. Basically, you could have all the calculations you want in your Python code. If you never tell it to print the information, it's all going to stay locked away inside the computer. You, the human, never get to visualize it then. So you take the print function and you place inside the parentheses the thing you want it to print, the computation you want it to output. In this case, I want it to output 3 plus 2. I happen to know the answer to that is 5, and I'm glad to see Python gets the same answer here with 5. Next line, I see a 3 minus 2. Well, I know the answer to that is 1. Python gives me a 1. Then I do 3 times 2. I get a 6, and you probably guessed it, 3 divided by 2. Python gives me a 1.5. It even knows how to handle decimal places, just like your graphing calculator does. So far, this probably looks a lot like your graphing calculator. It can handle addition, subtraction, multiplication, division. It can handle more complicated math operations. It can do sine and cosine. It can do square roots. It can do powers. But for right now, we're just going to stick with the basics so that we don't overload your input there. And again, I want you to notice that Python carries out all of this in order, right? So first was the addition, subtraction, multiplication, division, and that's the order in which it appears here. I can even add more print statements, so I could just tell it to print a banner of equal signs. So if you're ever having trouble figuring out what it is that your code is printing, you can print a little message for yourself in quotation marks like this. It will take what's in the quotation marks and just print that literally to the screen as it appears. And so I get my little banner here so I know where I'm starting. And then I'm going to have it print 1, 2, 3, 4, 5. Sure enough, it goes in order 1, 2, 3, 4, 5. Right. The important thing here is that Python can handle calculations for you, and it will do them in the order that you tell it. So then I give you an opportunity to try this out. There are these checkpoints throughout this tutorial that just ask you to modify the code. I will very rarely ask you to create new code. I usually ask you to either modify it or copy and paste and make a slight change. Here's the example we're going to talk about throughout this tutorial, is calculating square root of 2. Now, I already mentioned there is a square root function, which is good because we need that to get that quickly. But it's always good when you're first learning to do something with a programming language to try out a problem you know the answer to, because if you start out with the unknown, you have no way of knowing whether your answer at the end is appropriate, right? So if we get 1.414, etc., we know that we are on the right track for square root of 2. The way we're going to do this, here's just a little bit of a calculus review, is using a Taylor series. I include a link here to Math World where you can refresh yourself on Taylor series. But the basic idea is that if you want to take a function and make an approximate version of it, you can do that by having the function at a certain value c, plus the first derivative, plus the second derivative, plus the third derivative, multiplied by the appropriate factors. So there's a 1 over the number of derivatives factorial. So second derivative gets 2 factorial, third derivative gets 3 factorial. And then you multiply by x minus c squared. Remember, c is the point that you're expanding the Taylor series around. So that's your central point that you start at. And then x is the point near c that you're trying to investigate. And so you might see x minus c gets a linear term, then a square term, then a third term. So all the numbers match up, right? It's 2 factorial, second derivative, second power, third factorial, third derivative, third power, etc. So for this particular case, for the case of f of x equals square root, we can approximate square root of x with these particulars, right? So there's going to be our factorials, 1 over 1 factorial, 2 factorial, 3 factorial, etc. Then we have to do the derivatives, right? And the derivatives are always evaluated at c. So the goal is for us to pick a number whose square root is easy to work with. I can't think of a better number for that than 1, because square root of 1 is 1, and 1 to any power is 1, so that'll be nice and easy to work with. So if we want to expand this around c, we take our root c, that's just f at c. We take 1 over 1 factorial, and then the derivative of f evaluated at c. So the derivative for this thing is going to spit out a 1/2 and lower the power here. It's going to be root c to the minus 1. And I'm leaving it as root c. Instead of calling it to the minus 1/2 power, I'm leaving it as root c for a very specific reason. We'll see why that is in a few minutes. Here we spit out another half, we flip the sign. Here we spit out 3 halves, we flip the sign again. There's a pattern to it. We're going to use that pattern over the course of this tutorial. So the way I could do this, I could just take all of these values and plug them in here in a code cell, right? So for one term, if I just take the first order term, I would get square root of c. I happen to know the square root of 1 is 1, so I would have 1 here. Wonderful, earth-shattering math, I know. For the next one, we're going to say 2 terms. So I have a 1 over 1 factorial. There's that piece. I have a 1 over 2. There's that piece. I have a square root of 1 over 1, which is going to, or in the denominator, excuse me, so that's going to be a 1 here. Then I take 2 minus 1. That's my x minus c here. And so when I run this, I'll get out these 3 answers. I'll get out the 1-term answer, the 2-term answer. I even have a 3-term answer. And it's really getting hairy here, right? Because I have to take this piece, copy and paste it. Then I have to tack on the next piece. I have to tack on the second order term. So I have a 1 over 2 factorial, 2 1/2, a 1 to the negative 3 power, and then x minus c squared. So I've got 2 copies of x minus c right there. And so I start out with a really bad approximation, right? 1 is a terrible approximation for a square root of 2. 1.5 is okay, right? Because the real answer is 1.4 and some change. So this is actually better. 1.375, I'm at least getting more decimal places. It'll probably get better on the next one. Speaking of the next one, that is your goal in this step, is to copy and paste these 2 lines. Lines 7 and 8, paste them here at line 11, and then add on the next term, right? So I've done the first 3 terms, the 0th order term, first order, second order. I'm asking you to add the 3rd order term. So you can just copy all this down. You have 1 over 3 factorial. I bet you can find out what 3 factorial is. 2 factors of a half, a factor of 3 halves. 1 to the negative 5 power, and then x minus c to the third power. And so that will get you an even better approximation for the square root of 2. It should come out to 1.4375 if you put everything out there appropriately. That should be the answer that you arrive at. So that's kind of cool. We can successfully get close to the square root of 2. I can carry out all this stuff mathematically, and I don't have to type it over and over again. But let's be honest, this is kind of cumbersome, right? I am having a difficult time keeping track of what each of these 2's is, what each of the 1's is, whether it's supposed to be a plus or a minus, how many terms I have, etc. This is nice, but it is getting cumbersome. This is why we have variables. So this next step walks you through how we use variables in a code. The idea of a variable is that I'm taking a number, and I know what the number's value is, but I don't want to have to write that number again and again and again. I want to be able to just say that that number is a. So for example, here, I take a and set it equal to 2. That's basically what this means, is I have a number on the right, and I just store that number under the name a. Then I can do math with that a, just like as if I were writing it out in algebra class. I can type out stuff here, so I can have print a times a times a times a times a times a times a. And you might not be surprised. Here you get the powers of 2, right? So I get 2, 2 times 2, 2 times 2 times 2, etc. Because a equals 2. So it's taking that 2 and plugging it in for a everywhere. Now, at first glance, this really isn't that much different because I know a equals 2. I might as well just write 2 over here. Here is where the advantage comes in. Let's suppose instead of the powers of 2, I wanted the powers of 3. All I have to do now is change that a to a 3 and click Run. Because it already has all of the math, all of the operations stored in a. If I were to write this out as 2, 2 times 2, 2 times 2 times 2, etc., I would have to change every single one of those 2's to a 3. And that's cumbersome. That's a time waster. Instead, I can just declare the variable 1 stored under that name, and then write out what I want to have happen to it. And then I'm free to change this to other numbers. I could change this to 4. Lo and behold, I get the powers of 4. I could change this to a half. Right? I could get the powers of a half. There's a half squared, a half cubed, a half to the 4th power. It's really useful because all I have to do is make that one change and the rest of the code takes care of itself. So if you want to think about it, it's like we're separating the values from the operations that we're carrying out. It allows me to separate those two actions so that I can manage the problem a lot better. Well, we can use variables to make our calculation of square root of 2 much easier, right? Because I had all these 1's and 2's flying around, and it's really difficult to keep track of what all the 2's are. Like, is that just from a half from the derivative, or is it a 2 meaning the value of the square root that I want? Right? And so what we can do is declare some variables. So here I've got the exact same calculation as before. When I run this, it's going to give me the exact same answers that we had before for our 1-term, 2-term, 3 terms. But instead I've written it in terms of variables. So first I've defined square root of c, right? I need to know what square root of c is because I'm going to be using it over and over again. If it's a number you're going to use more than once, it should get a variable name. I define what c is here. Right, because I need to reference that in my x minus c. And then I can define my x here. And now here's where it gets great, because now I could change that 2 to a 3 and get the square root of 3 instead. Or I could change it to a 7 and get square root of 7, right? So I go through the same process. I have one term is just the square root of c. That's going to give me a 1 here. I have two terms equals all of this, square root of c plus 1 over 1 factorial times the half from the derivative divided by square root of c times x minus c, right? And the other advantage to this is this looks very similar to the math that we wrote up here. One of the reasons we use variables is so that I can compare it to the math equation a lot easier, right? I can see here I have 1 over 1 factorial, 1 over 2, root c to the negative 1, and x minus c. I can compare that down here. And that's exactly what I have. 1 over 1 factorial, 1 over 2, 1 over root c, and x minus c. So then when I go to 3 terms, it looks like the equation. I'm not having to keep track of what all the 1's and 2's are. I just literally type out what I had in the equation. It's a little bit different because I have to give things names. So like I call it square root of c because that's what it is. It's the square root of c that I had in the equation. Always give your variables names that make sense. Don't just call a variable x, unless it is the x coordinate. Always give it a name that makes sense. Python can handle names of, I think, just about any length. I've never run into an issue where the name was too long. So you can always give it a specific name that you can read later. Your future self will thank you. So here what I ask you to do is to copy and paste lines 10 and 11, and then add the fourth term, which is going to be even easier now because you can just write it in terms of square root of c, etc. Like I said, you can also change this to get, say, for example, square root of 3. Looky there, I'm getting close to square root of 3. That one's a little bit farther off. Or I can do square root of 4, right? Always start with an answer, with a question you know the answer to. I actually get it correct here, and then it overcorrects there. So we definitely need some more terms to find out our answer there. But after that, it gets even better because these variable values, they are not set in stone. Once you set a equal to 3, it's not locked in, right? You can change the value of a later if you need to. For example, let's suppose I ran this code where I had a equals 7. And then I said, you know what? I need a to be twice as big as it was before. I can write a equals 2a. Now, if you're just coming out of a math class, that looks like mathematical heresy because you look at that and you say, how can a equal 2a? Oh, a must equal 0. That's the only number it works with. No, a equals 7. Well, how does a equal 7 and a equal 0? That's because this equal sign, remember, is not an equality. It's not saying a equals 2a. It's an assignment. It says, take the thing on the right, calculate it, get me a number, and store that number in A. Store that value in A. So it's like you have a file on your computer. You write on that file, and then you save over the file name, right? You don't need the old version, you need the new version. You're always saving over your old file name. That's what's going on here. You're saving a new value under the name A. And in this case, it would give you an output of 14. And you can do this as many times as you want. Let's suppose we wanted to get the powers of 2 again. Well, I can do that from here because each time I'm taking output and multiplying it by A. I'm multiplying it by 2 again. So I would get 2, 4, 8, 16. And this one's really nice because I don't have to change it every time, right? I can literally copy and paste this one thing as many times as I want, and then it will keep multiplying it by 2. So basically, each time this goes down a line, it's going to multiply output by 2 again. Or again, I could change this 2 to a 3, and then I get the powers of 3 really easily. So what does this do for us with square root of 2? Well, remember, we're making successively better approximations to the square root of 2. It would be nice if I didn't have to recalculate those first 2 terms every single time. So here what we do, we're taking our current approximation, our one-term approximation, and we're storing it as square root of x. Then we're taking our 2-term approximation and we're saving it as square root of x. Then we're taking our 3-term approximation and we're storing that as square root of x. So the only thing I ever print is square root of x. So this is cleaning up the print statement a little bit, right? We're separating the calculation from the print statement, which is nice. And again, you'll notice I get the exact same results as before. So there's another checkpoint here for you to try out using variable reassignment. I'm going to ask you to start in line 18 and make your own calculation out to 3 terms, and then just print square root of x, right? Update the value of square root of x. And then there's a section here. I'm going to let you read this on common errors to watch out for. We inevitably make mistakes while preparing a code. I have here in the tutorial examples of 2 errors that I managed to generate completely by accident while developing this tutorial. What Python will do is try to tell you where the error is, but it doesn't always do it in the most helpful way. And so this section here just walks you through the process of learning how to read error messages, learning how to fix them, and frankly, learning how to ask for help with them. So you can always search online for an error. You can always ask your instructor or your classmates. I guarantee you, you're not the first person to see an error that comes across your screen. And then finally, this tutorial concludes with an exercise for you to finish out this code that calculates gravitational potential energy. If you're not familiar with it, gravitational potential energy is how much potential energy is stored in the interaction between two celestial bodies out there in space where they have masses m1 and m2. There's a universal gravitation constant g and the distance between the two objects r. What I'm asking you to do is fill out the rest of this information. I give you the universal gravitation constant. I give you the mass of the sun here. You could change that value if you want to. And then I'm asking you to fill in m2 and r. And then I want you to create the calculation for u here. Maybe you want to put it all in one line. Maybe you want to just put u equals negative g and then do updates. You do it however you want. Just carry out this calculation here, answer those questions, and you will be well on your way to success in computational physics.